You know, that incredibly frustrating, basically universal experience of sitting down in your car, turning the key, and locking eyes with that little static cling sticker.
Oh yeah, the oil change reminder in the corner of the windshield.
Right, exactly. Or maybe you're someone who relies on, like, an automated calendar alert on your phone. But either way, if you really think about it, you are basing a crucial piece of mechanical maintenance on a total guess.
Yeah, a complete assumption.
Right, because it's been 3 months or, 3,000 miles, so we just assume the oil must be bad. But what if you never had to guess? Like, what if your car's engine could monitor its exact internal strain, log every single rotation, and tell you precisely, down to the millisecond, when its components were degrading?
I mean, it would completely upend how we interact with machines. We'd instantly move away from arbitrary timelines and step into this world of absolute unyielding precision. And while consumer vehicles might not be entirely there just yet, but that merciless precision is exactly what runs the heavy industrial world.
Because when downtime costs tens of thousands of dollars a minute,
Exactly. Guessing just isn't a viable financial strategy.
which brings us to the core of today's deep dive. We are looking at a highly technical implementation strategy for industrial controllers. Specifically, we're focusing on a document covering Logic's PLC runtime monitoring and this architecture known as the AOI underscore Elapsed underscore time strategy.
It's a fascinating playbook.
It really is, and our mission here is to decode it. We want to uncover how modern manufacturing facilities use precise, self-auditing logic to save massive amounts of money, prevent disasters, and just work smarter.
To really grasp the sheer scale of what this strategy accomplishes, we first have to, establish the environment. We're talking about the domain of the PLC, which is the programmable logic controller.
Right, for anyone who hasn't spent time on a high-speed factory floor, what is that?
You can picture a PLC as the ruggedized digital brain of the operation. It's an industrial computer tasked with making thousands of instantaneous logic decisions every single second just to control heavy machinery. And this specific runtime document is basically a master class in how to program that digital brain to track time perfectly.
I want to look at the real-world problems this code actually solves because, well, initially programming a clock sounds deceptively simple.
Right, you just count seconds.
Exactly, you just count. But the strategy here details a massive shift in manufacturing. It outlines the move from reactive or calendar-based maintenance to what's known as usage-based maintenance.
And that is a fundamental shift in how a business handles its physical assets. The core idea is you only replace components, like heavy-duty bearings or mechanical seals, based on actual verified operating hours, not just what a calendar dictates.
Which obviously impacts OpEx, right? Operating expenses.
Oh, massively. Consider the financial weight of it. If your protocol says you have to replace a highly specialized industrial bearing every 6 months, you do it to be safe. But if that line hasn't been running at full capacity, you might be throwing away a component that still has, like, 40% of its operational life left.
So you're just bleeding money to buy peace of mind.
Exactly. Multiply that across a whole facility, and it's a massive hit. But let's look at the flip side, which is arguably worse. Say that same machine has been running double shifts, heavy loads. You're waiting for that 6-month mark on the calendar.
But at month 5, the bearing just shatters.
Yes. The entire production line grinds to a halt. Product is backing up, workers are standing around, and you are losing hundreds of thousands of dollars. Usage-based maintenance bypasses both nightmares by tracking the literal physical hours the machine is moving.
And it goes deeper than just broad machine movement, right? The source talks about critical cycle monitoring.
Yeah, this is where we get into the lifespan of individual consumables. Take industrial UV lamps for curing adhesives, or copper welding tips on a robotic arm. These aren't just gears turning, they degrade strictly through active deployment.
Like a UV lamp might have power, but is it actively curing a product?
Precisely. A welding tip only experiences thermal degradation when the arc is actually struck. By monitoring those exact microcycles, a facility extracts the maximum value out of every single consumable.
That isolated tracking plays directly into OEE analysis too, right? Overall equipment effectiveness.
Yeah, the system does automatic data logging. It's constantly comparing active RUN time against ideal time. There's no supervisor walking around with a clipboard and a stopwatch. The machine is conducting a relentless audit of its own productivity.
But the part of this that genuinely stopped me in my tracks was preventive diagnostics.
Oh, this is where it shifts from just recording data to actively interpreting mechanical health.
Right, because the architecture specifically looks at measuring actuator stroke times. It watches the physical movement of pneumatic cylinders to detect, like, mechanical degradation or invisible air leaks. Let me try to contextualize this for you because the implications are
So
huge.
go for it.
Imagine you time yourself walking up the exact same flight of stairs in your house every morning. Normally, it takes exactly 10 seconds. You have a baseline. But one morning, a stopwatch notices it suddenly takes you 13 seconds. The next week, 14.
Right, you haven't collapsed.
Exactly. You haven't broken a leg, you're still getting to the top of the stairs. The process functions. But that extra time is a glaring red flag that something is systemically wrong. Maybe your knee is giving out, or you're getting sick.
That's a really solid analogy. But in an industrial setting, we can be much more precise about what that illness actually is. An actuator uses compressed air to push or pull mechanisms. If an actuator has a baseline stroke time of 2.6 seconds and the PLC suddenly logs it taking 2.5 seconds,
Your mission hasn't failed yet.
right, the widget is still being built. But that extra half second is an incredibly loud alarm. It tells the engineering team the internal seals are wearing out, letting air bypass, or maybe the grease on the rails is dried up.
So the system is effectively predicting its own death weeks before a component literally snaps in half.
Yeah. You could schedule a mechanic to swap that actuator out during a routine lunch break rather than having it blow apart and shut down the whole plant on a random Tuesday.
It transitions a facility from this chaotic, reactive posture to a highly controlled, proactive intelligence. But getting that intelligence across a massive facility introduces a totally new problem.
Scale. Oh, massive scale issues.
Because if a factory needs to track the independent runtimes for 10,000 UV lamps, filters, motors, I mean, the sheer volume of code would be staggering. Having a programmer write custom timer logic from scratch for every single component would be a nightmare.
It would be functionally impossible. You'd end up with miles of spaghetti code, which is just an absolute breeding ground for human error. One misplaced decimal point could throw off a critical system's maintenance schedule, which is why this strategy revolves around the deployment of an AOI.
The add-on instruction. This seems to be the magic bullet of the entire architecture. And the first major advantage it offers is standardization.
Think of it as a highly complex digital cookie cutter. Instead of an engineer writing out timer logic, verifying math, and linking variables every time they want to monitor a new motor, they build the perfect logic structure exactly one time.
They validate that one block and then just stamp it out.
Exactly. Stamped out wherever they need it.
Which instantly solves the scalability problem. You install a new packaging line with 50 different conveyor rollers. You don't rewrite code, you just drop the AOI onto each one, and they are immediately tracking time. But here is where I kind of have to throw a flag and push back on this strategy a bit.
Okay, what's the issue?
The implementation heavily emphasizes encapsulation as a key advantage of the AOI. It locks away all the internal background calculations. Now, encapsulation sounds like a very polite engineering word for a black box.
It does, yeah.
And if I'm a maintenance tech on the floor and a machine goes down, I hate black boxes. If you hide the logic, aren't you locking the mechanic out of the engine? How are they supposed to troubleshoot a system they aren't allowed to see?
That's a very fair criticism. The tension between open source accessibility and lockdown systems is a constant debate. But in these specific environments, that black box is non-negotiable.
Really? Why?
You have to consider the reality of a multi-million-dollar facility. Over 5 years, you might have 20 different technicians going online with that PLC to troubleshoot completely unrelated issues.
Oh, I see. So you're saying the threat isn't the machine, the threat is the people working on the machine.
Exactly. Without encapsulation, the raw math governing how the plant tracks maintenance is just sitting out in the open. A junior technician, trying to quickly bypass a faulty safety sensor at 3:00 a.m., might accidentally alter a timer preset, or just delete the run of code that converts seconds into hours.
Yikes. So by locking it down, you establish a perimeter.
Yes. You protect the integrity of the data from accidental human spoliation. You ensure standardization across the entire plant.
Okay, I see the angle. You are prioritizing the systemic integrity of the data over the convenience of individual troubleshooting. You want the dashboard to be perfectly reliable, so you just weld the hood shut.
And that leads directly into the HMI integration, right? The human-machine interface.
Mm-hmm.
Because the AOI is encapsulated, it guarantees a totally uniform data structure.
Right. If every timer outputs data in the exact same format, building the visual interface is super streamlined. So let's actually look under the hood of that black box then. How does it process raw, chaotic machine states into human-readable alerts? The architecture is broken down into inputs, outputs, and the internal logic engine.
Right, so the process starts with the inputs, which are raw triggers from the physical world. The primary trigger is enable_timer, which is a simple Boolean bit.
A true or false state.
Exactly.
Hmm.
Is the primary drive motor actively receiving power? Yes or no? Then we have the reset_acum Boolean. This is the manual override triggered by a technician after they perform maintenance to clear the slate.
And governing all of this is the preset_time, which is the target threshold, usually in hours. If a UV lamp is rated for 2,000 hours, your preset is 2,000. So those real-world inputs feed into the engine, which relies on something called an RTO.
The retentive timer on. This is the fundamental building block of industrial timekeeping.
And retentive is the operative word here, right? It retains its memory.
This is absolutely critical. If you use a standard non-retentive timer, it wipes its memory the second the conditions drop. If a machine runs for 5 hours and then there's a microstoppage, say a safety door opens for 3 seconds to clear a jam, a standard timer resets to 0.
Oh, wow. So you'd completely lose those 5 hours of wear and tear data.
Exactly. But an RTO does not forget. When that safety door opens, the timer just pauses. When the door closes and the machine restarts, it picks up right where it left off. It survives power outages, emergency stops, everything.
So the controller looks for 2 conditions. The motor must be running and the maintenance reset cannot be active. As long as those are met, the RTO ticks up. When it hits exactly 1 second, it adds a single integer to a running tally called total_seconds, then resets itself and starts counting the next second.
It's an endless, relentless loop, building a massive pile of raw seconds.
But this is where we hit the visualization problem. The PLC is perfectly happy holding like 86,400 raw seconds in its memory, but if a mechanic looks at a screen and it just says, current runtime, 86,400 seconds, that is completely useless.
Right, the system has to translate machine logic back into human logic.
It has to peel the onion, basically. Strip away the massive numbers and break them down into recognizable hours, minutes, and seconds. And the mathematical bridge it uses to do this relies heavily on the modulo operator.
Modulo is an incredibly elegant tool for this. When you divide a number, you get a whole number and a remainder. Modulo isolates that remainder. It basically asks, after you pull out all the perfectly full blocks of time, how many raw seconds are left over?
Let's walk through that because the structural logic is fascinating. The first step is easy. To find the total hours, you take your massive pile of total_seconds and simply divide by 3,600. You know, there are 3,600 seconds in an hour.
Easy enough, but you can't just divide by 60 to get your minutes.
Right, because that would give you the total minutes the machine has ever run, which is another massive, unreadable number.
Exactly. You only want the minutes that belong to the current incomplete hour. So you apply the modulo operator, you take the total_seconds, and you apply modulo 3,600. The logic strips away every single full hour, throws them aside, and isolates only the raw seconds that are left over.
Leaving you with a much smaller pile of seconds that weren't quite big enough to make a full hour. So you take that leftover pile, divide it by 60, and boom, you have your exact minutes, from 0 to 59.
And the final step isolates the seconds the exact same way. You take the absolute total of accumulated seconds and you apply modulo 60. You strip away every full hour, every full minute, and whatever fractional remainder is sitting there, those are your precise seconds.
Perfectly formatted for a human to read on a screen.
Mm-hmm.
It takes this abstract accumulation of machine data and seamlessly translates it into a digital clock. But the AOI doesn't stop there. It provides 2 final status outputs that make this an active diagnostic tool. %_progress and alarm_ready.
Yes, the crucial outputs.
%_progress outputs a clean percentage from 0 to 100, representing the consumed service life. When I was looking through this, I couldn't help but picture the UI of a video game.
Like a health bar.
Exactly. It acts exactly like a health bar for physical machines. An operator isn't doing mental math on how many hours are left. They are watching a visual health bar slowly drain or fill up. You can be 50 feet away, glance at a monitor, and instantly see that a drive motor is at 96% consumed life because its health bar is pulsing red.
It distills millions of data points into instant visual intuition. And that alarm_ready bit is the ultimate trigger. When that health bar hits 100%, that Boolean bit flips to true. It can automatically generate a work order, flash a light on the factory floor, or send an email to the plant manager.
It takes all that encapsulated math and forces human action before a failure can occur. When you step back and look at the whole picture, the transformation is incredible. We started with this expensive problem of unpredictable chaos, factories replacing perfectly good parts out of fear, or just letting machines tear themselves apart.
And the solution is an exercise in rigorous, scalable logic. A single block of encapsulated code turns continuous machine time into actionable intelligence. By isolating RON time versus IDL time, tracking critical microcycles, and using modulo math, it fundamentally optimizes physical production. It saves money, preserves uptime, and just completely eliminates the need to guess.
It's the ultimate application of logic to physical chaos. Which actually brings me to a final thought I want to leave you with today.
Yeah.
We've just spent this entire deep dive unpacking how a flawless digital system monitors the critical cycles of industrial machines. We looked at how it calculates the exact percentage of consumed life to perfectly optimize a factory's output, tracking every millisecond of strain.
Right.
But consider the trajectory of this technology. If our systems are this adept at logging the exact RUN versus IDL time for a conveyor belt, if the math is this flawless at tracking mechanical strain without the machine ever knowing it's being watched, how long before we see this exact same percent underscore progress logic integrated into human workflows?
Oh.
Right. How long before the corporate networks we log into every day are quietly calculating the service life, the microcycles, and the exact RUN versus IDLE time of our own daily productivity? It is definitely something to keep in mind the next time you decide to pause at your desk just to catch your breath.